Okay, so density. Density is the ratio of the mass of something to its volume. So we can write an equation to describe density. Density equals mass divided by volume, or using just symbols instead of words, D equals M over V. Density is a fundamental property of substances. Different substances have different densities. That's why when you pick up a box, an empty box, it's very light because the density is low, and you pick up a brick and for the same size, the same volume, it seems very heavy, right? Because the density is different. If you change the size of an object, the density doesn't change. If you think about a big 2x4 perhaps, it has a certain density. If you cut it in half, you now have two pieces. Each piece weighs less, but the volume is also less. And since density is a ratio, the density stays the same. So density has nothing to do with the size of the object. It's an intrinsic property of the substance itself. So we can calculate the density by taking the mass and dividing by the volume. So just a simple example of that. A sample of a liquid has a volume of 22.5 milliliters and a mass of 27.2 grams. Calculate the density. So the density is the mass divided by the volume. So we write the mass in the numerator, 27.2 grams, divided by the volume, 22.5 milliliters. We use our calculator to do the math, bless you. 27.2 divided by 22.5. My calculator is giving me a really long number. How many significant figures should the density have?
3.
It should have 3 because the mass and the volume each have 3. So as I'm writing down what my calculator says, 1.20, I'm just making a note that, okay, that's the third sig fig, that's where I'm going to stop. And then I'm just going to write down 2 extras, 8, and the next one's an 8 and an 8, and that would round up. What would the unit on that be? Grams per milliliter. Because they don't cancel out, and there's no converting between them or anything. They just sit there. That's fine. And then I'm going to write the rounded version. It's going to round to 1.21 grams per milliliter. And that's the density of that liquid. Any questions? So we'll be doing problems involving density. The solution map here is when we're calculating a density, involves an equation rather than a conversion factor. You're starting with a mass and a volume, like we just did, and to calculate the density, we need to use an equation. Here's another one. A customer purchases a platinum ring that has a mass of 9.67 grams and displaces 0.452 cubic centimeters of water. Is the ring genuine? And then we're given the density of platinum. Platinum always has the same density. So if the ring is made out of platinum, its density should match the known density of platinum. Doesn't matter how thick or thin, how large or small the ring is. So we need to calculate the density. So we're given the mass and the volume. Oops. Double oops. Twitchy fingers this morning. So here we have a mass. And when it says it displaces this much water, the word volume doesn't come into this problem at all, does it? It doesn't say anything about the volume. Displacement is a method of finding the volume of an irregular object. If you have, say, a cup that's half full of water, maybe a measuring cup, and it says half a cup, and you put an object into it, what's going to happen to the level of the water? It rises. Does that mean there's more water in the cup? No. The object that you put in pushed away or displaced the water. And so the on the measuring cup, how far the water went up, the apparent change in volume of the water is actually equal to the volume of the object. So that's what it means by displacing. So if you didn't recognize what that meant, you could look at this unit, cubic centimeters, and you should recognize that as a unit of volume. So this is the volume over here. So we need to find the density. So we need the equation. Density equals mass divided by volume. Mass is 9.67 grams. Volume is 0.452 cubic centimeters. And then we get out the calculator again. 9.67 divided by 0.452. Because the mass and the volume each have 3 significant figures, this result should also have 3. And the units, nothing cancels out, grams per cubic centimeter. We round that to the correct number of significant figures, we get 21.4 grams per cubic centimeter. It's the density of the ring. Is it platinum? Yep, it is. It happens to match exactly. What if we got 21.3? Do you think that would still be platinum? Yeah, because when we look at this number, there is uncertainty in the last digit. The mass and the volume were measured. There is error in every measurement, okay? That's one of the purposes of keeping track of significant figures, because my calculator said it was 21.39380,531 grams per cubic centimeter. Well, is it really that precise? No, because each of these had uncertainty in the third significant figure. So the rules of sig figs allow us to round it so that this density reflects the actual uncertainty based on the measurements. Any questions? So the ring is platinum. Answer, yes. Genuine. So some density equations density problems require the use of the density equation. If you're asked to calculate the density, you have to use the equation. If you're given a density and asked to find the mass or the volume, the density works as a very nice conversion factor. It can also be done using algebra and the density equation, but in my experience, which is considerable with Chem 3A students, a lot of them solve the equation incorrectly and end up with the incorrect answer. It's actually much simpler to use the conversion factor method. So that's what I'm going to teach you. So for a liquid substance with a density of 1.32 grams per cubic centimeter, what volume should be measured to deliver a mass of 68.4 grams? So we need to sort and strategize. So sorting, we've got these numbers. We read the we read the problem, and now we'll write out the numbers. So 1.32. This unit here is written all on one line because it's much easier to type into the computer that way. But this is grams per cubic centimeter. That's actually a fraction. So when you write that down with your hand and your pencil, make it a vertical fraction to tell your brain this is a fraction. Otherwise, funny things happen. So grams per cubic centimeter. And then the other number that we're given is 68.4 grams. So we've got two numbers. We have to decide which one are we going to start with. Well, this one looks like a conversion factor, doesn't it? The density gives the relationship between grams and cubic centimeters for this particular substance. We are given grams, and we're asked to find volume. What volume? So from grams, we want to go to volume. Now, it doesn't give us a particular unit for volume. What would be a really convenient unit to use here? cubic centimeters. The density is already in grams per cubic centimeters. Cubic centimeters is a perfectly valid unit of volume, so let's just use that one. So this is a dimensional analysis problem instead of an algebra problem. I know many of you don't care for algebra that much, so here you can avoid it. So 68.4 grams, one arrow, one conversion factor. So we've got grams to cubic centimeters. Grams, and we're going to put cubic centimeters on the top. And then I want grams to go away, so I'm going to divide by grams, because in that way, the grams will cancel out. So just like what we did yesterday, we're letting the units tell us what to do. Now we look at the density, and we see that there's no number in front of cubic centimeters. That may bother you. If it bothers you, put a 1 there. And there's a 1.32 with the gram. So down here where gram is, I'm going to write 1.32. There's no number up here. That's okay. Or if it bothers you, put a 1 up there. Doesn't change anything. I don't have to rearrange an equation. I don't have to think about, was I supposed to multiply or divide? The units told me what to do. So 68.4 divided by 1.32. How many sig figs should this answer have? 3. You'll notice a pattern that most of our example problems are going to end up with 3 sig figs. And then the unit is what? Cubic centimeters. So when I round that then, 51.8 cubic centimeters. That's the volume that I need. Any questions?
As far as the density, the number is always with grams, and then it's just over cubic, it's over the volume?
Yeah, for densities, it's always grams per cubic centimeter, and we're indicating that 1.32 grams per 1 cubic centimeter. It's a lot like a rate of speed, you know, if you're traveling 70 miles per hour. Well, how many miles do you go in 1 hour? 70 miles. We say that and we use that unit so frequently that we don't stop and think about what it means. But 70 miles per hour is also a very useful conversion factor if you need to know how long it's going to take you to drive, 240 miles or whatever. Any other questions? So this table, excuse me, all choked up about density this morning. This table is from your textbook. It gives the densities in grams per cubic centimeters for several different substances. Many of these are elements, some of them are not. You do not need to memorize any densities except for one, and it's really an easy one. I do expect you to remember the density of liquid water, which is 1 gram per cubic centimeter. That's not a coincidence. Water was used in the development of many of the units, and so it's not a coincidence that it's 1 gram per cubic centimeter. But the density of water is 1. That makes calculations with water really simple. But the rest of these, if you needed them in an exam, I'd give them to you. On homework problems or lab problems, you might have to go look those up. They might not be given to you. You just have to go look for it, okay? Do another example. Drop of acetone, that's the important ingredient in nail polish remover, has a mass of 35 milligrams and a density of 0.788 grams per cubic centimeter. What is its volume in cubic centimeters? So this question is a little nicer because it actually gives us a unit to look for. Well, let's write these numbers down. Always a good strategy. 35 milligrams and 0.788 grams. Write this as a vertical fraction instead of just a slash. And those are the numbers. So we've got 35 milligrams and we've got 0.788 grams per cubic centimeter. So if you struggle with questions like this, one of the dilemmas that you have is, which is the one that I start with? So it is almost always the one with a single unit. This is just a single unit, milligram. This has 2 units with a per in there, grams per cubic centimeter. That's almost always going to be your conversion factor. So this is the one we start with. So we need to figure out a path here, 35 milligrams, and what are we trying to find? Now, ultimately, what is the volume in cubic centimeters? Okay, so we're looking for cubic centimeters. Let's look over here. Can we go directly from milligrams to cubic centimeters using the density? No. The density has grams per cubic centimeters. So if we had the mass in grams, we could use the density to get the volume. Can we convert milligrams to grams? Sure we can. So there's our path. Once you get the path together, you should be set. It's just learning to follow the path, right? Some people aren't good at following maps, but this is a map you can learn how to follow. 2 arrows, 2 fractions. So I look at my path, milligrams to grams to cubic centimeters. So milligrams to grams to cubic centimeters. I'm just copying it down. I need this unit to go away, so I'm going to divide by it over here, milligrams. So those would cancel out. I need grams to go away, so I'm going to divide over here. And that's how I get the units together. Units first. Now we stick numbers in. You don't have to do it in any particular order. I usually go with what's easiest or occurs to me first. Well, here the numbers are just sitting there, right? 0.788 grams per cubic centimeter. 0.788 grams. So down here where gram is, I need to write 0.788. And then if you want to, put a 1 up there, if it bothers you that there's no number. So that one's good. Now this one, you gotta be careful with this. What does the prefix milli mean? 10 to the what? 10 to the negative 3. So I've got, in these conversion factors, what's on the top has to be equal to what's on the bottom. So on the top I have gram, and on the bottom I have gram, so that's good. On the bottom I have milli. I could write milli on top, but that's not going to help my unit conversion. I'm going to write the numerical meaning of milli on the other side. So 10 to the minus 3. That's what milli stands for. Milli is like a nickname for 10 to the minus 3. It's shorter. So I've got 1 times 10 to the minus 3rd grams is equal to 1 times milligram, or 1 milligram. That's the pattern for doing all metric unit conversions with prefixes. Okay? So now I get out my calculator. Nope, that's my phone. I should be able to tell the difference. So I'm going to take 35. I'm going to multiply by the top there. On your calculator, you'd enter this as 1 EE negative 3. So 1 EE negative 3. And then you can multiply by 1 if you'd like, and divide by 0.788. How many sig figs is this one going to come out to have? 2. 35 milligrams is a measured quantity. It only has 2 sig figs. So my habit is to think about the sig figs, start writing down what the calculator shows me, underline the last significant figure that I'm supposed to keep, and then write 2 extras. Just in case I come back and realize that I screwed up, I don't have to put it in my calculator again. And then the unit, we look and we find the only unit that's not crossed off is cubic centimeters. And then my final answer, I'm going to round that 0.044 cubic centimeters. Any questions? Yes?
I'm sorry, you asked me, with the grams with the milligrams, so when you times the 35 times 1 EE negative 3, that's kind of like a division then?
It is like a division. It's the same as dividing by 1,000. And it is true that 1,000 milligrams equals 1 gram. And so you could use 1 gram per 1,000 milligrams, but I don't recommend that because I see a lot of students end up with it backwards. And they tell me 1,000 grams is a milligram. That's like telling me that 12 feet is the same length as 1 inch, right? We understand that that's ridiculous because we have a good understanding of how big inches and feet are. But when we're talking about milligrams and grams, it just doesn't register that you're getting it backwards. If you follow this pattern, it always works. You memorize the prefix and what it means as a 10 to the something. You can memorize that. You learned the alphabet when you were 5, right? You can memorize this short list of things. And you put the prefix on one side of the fraction and you put the 10 to the whatever that matches on the other side of the fraction, and it works every single time and you don't even have to think about it. So you can do that calculation other ways, and if you're good at that, fine, you do that, but I'm not going to teach it to the class. Did that answer your question?
Yeah.
Yeah.
I know, I still understand how you got the G fraction.
The what?
The G fraction, how you have this solution method?
This one or this?
Yeah, that. I don't understand where that came from.
Where the G came from? So I knew I was starting at milligrams, and I needed to end up at cubic centimeters. And I don't have anything that relates them directly. So this is like I'm trying to get across the creek, and I can't jump across in one leap. I need to find a stepping stone in the middle. So I'm looking around, I'm seeing what's available here. Well, that's no help because that's what I'm starting with. Here's this conversion factor that I'm probably supposed to use. And I see that this relates grams and cubic centimeters. So I know that if I stuck gram in here, this would allow me to get from gram to cubic centimeters. And so then I look and see, well, can I get from milligrams to grams? Oh, sure, that's just the metric prefix thing. And so that's how I got to that. Sometimes this is a fairly simple one. We'll try to start out with simple ones.
It doesn't look like she's here, so we're gonna go to the office.
Okay.
If she does come, feel free to call us.
Okay, I'll do that. Sometimes you start at the beginning and you're like, I don't know what to do. And then you go to the end and you kind of work back from the end. It's a little bit like untangling a tangled piece of string or something. You kind of have to work from both ends until you figure it out in the middle. And that's why I say setting up this path is the key to solving the problem, and it's the most challenging for many students. Once you've got the path together, the rest of it tends to fall into place. Any other questions? Yeah.
Could you explain the conversion factor grams per gram?
Yeah, can I explain this again? So let me just do this. Let's get a fresh piece of paper here. So if I'm wanting to do grams, let's see, milligrams to grams. So let's think of it this way. If I have, in my conversion factors, the top has to equal the bottom, right? So if I said 1 milligram divided by 1 milligram, that is equal to 1, right? And that's what we need. Well, that doesn't accomplish anything, right? I want to have grams on top and milligrams on the bottom. So what I can do is, instead of where it says milli, I can put in what milli stands for. So I can take the milli out and write 10 to the 3 minus 3 instead. So now I've got 1 times 10 to the minus 3 grams divided by 1 milligram. Because in our list of metric prefixes, milli stands for 10 to the minus 3. Okay? So milli is like a nickname for this. Does that help? That's how all the metric conversions work. Any other questions? Okay, a pure gold bar displaces 0.82 liters of water. What is its mass in kilograms? And they're giving us the density of gold. So let's write these numbers down. 0.82 liters. And the other number there is 19.3. Again, that fraction, write it as a vertical fraction. So we've got two numbers that are given. Which is our starting place?
22.
The 0.82 liters. This is going to be a conversion factor. So we're starting with this one. And what unit are we trying to end up with? Kilograms. The question, what? What is the mass in kilograms? We're going to be going through some other units in between, but we need to establish the starting point and the ending point, and then we can figure out how to get from one to the other. So this one's a little more challenging. So here we've got liters, here we've got kilograms, and our conversion factor has neither of those units. What do we do? It's okay, we can do this. We can do this. Well, looking at these two, which of them most closely resembles one of these? Well, grams and kilograms, that looks the easiest, right? So if we had grams, we could get to kilograms just knowing what kilo stands for. Okay, so that's good. If we had grams, we could get to grams from cubic centimeters using the density. And then liters to cubic centimeters. Okay, this one's kind of a puzzle. This is an often overlooked, very simple conversion factor. 1 cubic centimeter is exactly the same as 1 milliliter. Okay, so you should put that on your flashcards. 1 cubic centimeter equals 1 milliliter. Would that be useful?
Yes.
Yeah, because here we've got liters, and with metric prefixes, we could go from liter to milliliter, and knowing that those are the same, we could go from milliliters to cubic centimeters. So the missing thing in here is milliliters. Not the only way you could get there, but it's what we're going to do. Any questions about how to get the path? Solving problems, these are problems, okay? They're not just simple questions that you're going to know the answer to immediately. You have to think about them and puzzle through them. If it doesn't just strike you as obvious, don't give up, okay? You need to work at it a little bit. And the more you work at it, the more you practice doing these, the easier it'll get. Okay, so there we've got our path. This is a long one, right? It's got 4 fractions in it. So we just have 4 conversion factors. 1, 2, 3, 4. We look at the path and we read the units. Liter, milliliter, cubic centimeter, gram, kilogram. That's a lot to remember, but we don't have to remember because it's actually written down. So liter to milliliter. The next unit is cubic centimeter. The next one is gram, and the last one is kilogram. I'm just copying down the path into my equation. Then I need these units to cancel out. So liter is here. I take this unit and I put it in the denominator of the next term. And I take milliliter and it goes into the denominator of the next term. So liters, and those are going to cancel out. And milliliters down here, those will cancel out. And cubic centimeters, those will cancel out. And grams. So my units are all playing nicely together. Now I put numbers in. You can do it in any order you want. This one is kind of jumping out at me. 1 cubic centimeter to 1 milliliter. Well, that one's easy. 1 and 1. Done. The other one that strikes me is the density, since it's just given to me there, 19.3 grams. So I put 19.3 with grams per cubic centimeter or per 1 cubic centimeter. You can throw a 1 in pretty much anywhere. Multiplying by 1 doesn't change anything. Now the first one and the last one involve metric prefixes. So here, remembering that we need the top to be equal to the bottom. So milli, we just dealt with milli, right? Milli is 10 to the minus 3. So I have milli on the top. I'm going to write what milli means on the bottom. 10 to the minus 3. And if I put ones in front of those things, it doesn't change anything, but it makes it a little more apparent what I'm supposed to do with my calculator. Because now I have a number in scientific notation that's easy to enter into the calculator. Going to this one at the end, what does kilo stand for? Kilo is 10 to the what? 10 to the positive 3. So here I've got kilo on top, and I put what kilo means on the bottom, 10 to the plus 3. And then, to make things more comfortable, I can just put ones in front. Any questions? Some students will say, well, I'd rather do 1,000. I'd rather put 1,000 into my calculator. We need to get comfortable with scientific notation because there will be numbers that are too large to enter as a decimal number. So you might as well just get comfortable with it now. So this would be 1 EE3. EE stands for times 10 to the. So you don't go 1 times 10 EE. You just go 1 EE3 for 1 times 10 to the third. So make sure that you're doing these calculations while I do them so that you can make sure that your calculator is understanding what you mean. It's always the calculator's fault if it's wrong. 0.82 divided by 1 EE minus 3 times 1 divided by 1 times 19.3 divided by 1 times 1. I leave those out, but you can do it if you want. Divided by 1 EE3. Okay, I don't have room to write the answer there, so I'll just write it down here. How many sig figs should this have? 2. Our starting number only has 2 significant figures. This is an exact conversion. That's an exact conversion. This is an exact conversion. Density is not exact. But this density has 3 sig figs, and our starting volume only had 2. So our final result has 2 sig figs. So there's the 2 sig figs, and then the next 2 digits, and the unit is kilogram. Don't be confused by the leading zeros and think that those are significant figures. If you count those as significant figures, you're going to end up rounding a lot of things off to 0. Nothing should ever round off to 0. So you could express this in decimal form, 1/6 kilograms. My philosophy is if the problem doesn't specifically require scientific notation, then either decimal or scientific notation is fine. In my opinion, scientific notation is never wrong. You could write anything in scientific notation. Just as my own personal guideline, I look at the number of zeros, and if I can't very easily see how many there are, I would like it in scientific notation. 4 is about the limit. Once I get up to 5 or 6, I have to get my finger out and count, and that makes me feel like a kindergartner and makes me feel stupid. So I'd rather just put it in scientific notation. So let's also put this in scientific notation. To do that, we're going to put the decimal point after the 1, 1.6. We have times 10 to the something kilograms. And to find the exponent, we're going to look at how many places over did the decimal get moved. 1, 2, 3, 4, 5. So the exponent is 5. Sorry, that's so small down in the corner. Should it be a positive exponent or negative? Negative. It's a very small number. I have negative feelings about small paychecks, right? So a negative exponent for a small number. So 0.000016 or 1.6 times 10 to the minus 5. Yes?
So either answer would be feasible on a test?
Yes. On my exams, the answers are multiple choice, so it would be one or the other. You wouldn't have to choose, but you need to be able to do both. Any other questions? I don't want to do that one. There we go.